Today we're talking about balancing chemical equations, and on Friday we're going to go over to the computer lab, and we're going to do a simulation with this. It's kind of a little game of balancing chemical equations, but it's going to help to make it really visual, which is really a nice thing to do. I'll probably throw the simulator up on the website this afternoon when I throw the video up, so that you can play with it ahead of time if you want, but we'll do that on Friday. Okay. So, the law of conservation of matter states what? Would you remind your neighbor what the law of conservation of matter says? Great. Sounds like everybody said the same thing. They said the law of conservation of matter states matter cannot be created or destroyed in a chemical reaction. So this has significance to us as we kind of continue on through our unit that we're calling stoichiometry, which has to do with determining relative numbers of atoms in chemical reactions. This has significance to us because what it tells us is that in a chemical reaction, however many atoms we started with at the beginning, we have to have the same amount at the end. We have to account for where all the atoms go. This is significant to us because it tells us however many moles of atoms we have at the beginning of the reaction is the same number of moles of atoms we have at the end. Now this doesn't mean we have the same number of molecules. For example, if I take hydrogen gas and oxygen gas and I ignite them, there will be a reaction in which they will form water. So we'll go from 2 molecules to 1 molecule. That doesn't violate the law of conservation of matter because we still have the same number of atoms on each side of the equation. Okay? And we're going to look at that reaction in a moment. So let's make a note of that because it seems to be pretty important. In a chemical reaction, atoms must be conserved. They cannot be created or destroyed, only rearranged. So in a balanced chemical equation, we have the same number of atoms on the reactants side as we do on the products. So, and if you're wondering what are the reactants and what are the products, we're going to talk about that in one moment. So let's think about the reaction between hydrogen gas and oxygen gas. So the reaction between hydrogen gas and oxygen gas might be written like this. Hydrogen is a diatomic element, meaning that you always find it with itself. so is oxygen, and they would react to form water. And that water would most likely be in a gaseous state. It would be water vapor, because this reaction, a combustion reaction, produces a lot of heat. So the water would come out most likely as a vapor, water vapor, as a gas. And then you could eventually condense it back down into a liquid if you want. Which one?
So since you have like two hydrogen and two oxygen, what is the fourth or the second oxygen?
Does everybody see the problem we have here? So we're going to pause on that for 1 second. We're going to come back to it, and we're going to talk about it. And there's a reason I left little gaps right here. Okay. But let's talk about these G's here, right here. What are we representing with the G's? Whenever you see a G like that following a chemical formula, represents that the physical state is a gas. So we could do the same thing for a liquid. We put an L after and would represent that that is a liquid. We would do the same thing for a solid. We put an S afterwards and it would represent that it's a solid. And the other state we often write is aqueous, because a lot of things aren't just liquids on their own. They're not pure liquids, they're mixtures. And aqueous is a mixture with water. So it means dissolved in water. And water is a very common solvent that we use to dissolve things in. And a lot of the times, the only way we can get a reaction is actually to introduce water into the process. All right, let's go back to Luciana's question. There's a problem with this equation. Would you all agree that over here on this side, we have two hydrogens? So we have hydrogen and hydrogen, and they're connected. It's a molecule. It's hydrogen bonded to hydrogen, H2. And we also have oxygen bonded to oxygen. So we have O2, and they're connected to each other. And then on the other side, we have hydrogen bonded to oxygen bonded to hydrogen. So we have two hydrogens bonded to an oxygen, and that's our water. And by the way, this is our reactants side, and this is our products side. These are the things that are reacting, and these are the things that we're producing. So we're good on hydrogens, right? We have one hydrogen, two hydrogens, one oxygen, then we have extra oxygen. It just disappeared. Where'd it go? That's the problem, right? There we see how that's a problem? We're missing an oxygen, and according to the law of conservation of matter, oxygens don't just disappear, so it's there. But do you see oxygen anywhere on the product side of this reaction? No. You only see water. So that oxygen isn't by itself, it's attached to a hydrogen and another hydrogen, but that's another problem, right? We've run into another problem. Because we've created matter now. So where did those hydrogens come from? They had to come from the reactant side. So that means that we needed another set of hydrogens on that side. Do we now have the same number of atoms on each side of the equation? Yeah. So the way that we represent this in a balanced chemical equation is by adding in what we call balancing coefficients. So these pink numbers I just drew up here, we call them our balancing coefficients. They're always whole number integers, okay, which is repetitive, but they're always whole numbers, and they're called the balancing coefficients. So these are our balancing coefficients. And they're always whole numbers. Okay? We can't have part of a molecule. So you can't have half of an oxygen. We couldn't put 1/2 here and call it good. Because oxygen is O2, it's a diatomic element. So you're going to find it as O2. Okay? So these balancing coefficients, they scale up and down how many molecules you have. Right? A lot of you are going to be able to just kind of logically reason your way through solving these. Okay? But if you come across one that you can't just kind of reason your way through, like here we're just kind of able to visually reason our way through, right? We have 4 hydrogens over here now. We have 4 hydrogens. We have 2 oxygens. We have 2 oxygens. So there are some steps that you can take, okay? These are just kind of general guidelines, okay? A lot of you, like I said, are going to be able to just kind of reason your way through these, and that's totally fine. But if you need a little extra guidance, there's these 4 steps I've got written out here on the back. So we're going to do a couple practice problems here. And we'll probably only get through one, but we're going to do at least one, and then we'll maybe pick up with the other one on Friday. Alright, so it says write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So you'll notice that as we read through that, I was underlining and circling things. What did I underline? The physical state of matter. We boxed the name of the compound or the element. What does "and" mean mathematically? "And" means sum or add together. Okay. To produce indicates that we're moving from the reactants side of the problem to the products side of the problem. The other way you see that is to form. Okay. And that's the indication that you're moving from one to the other. And when we say we're moving from one to the other, we use an arrow. Okay? Silicon carbide and carbon monoxide gas. So, would you take a moment with your neighbor, and would you try to write the chemical name or chemical formulas for each of these? And maybe we'll do something like this. We'll fill in the blank. Okay, so silicon dioxide and carbon go to produce silicon carbide and carbon monoxide. Would you take a moment and try to fill in those blanks? Oops. What do you think would go in there? We're not going to worry about the physical state yet. We're just going to worry about the physical state when we get to the end. Right? Just take a moment. This is step 1, where we write a skeletal equation, writing the chemical formula for each reactant and each product. So I'm hoping that you wrote down something like SiO2, which is silicon dioxide. Remember, the prefix di means 2. Carbon is just carbon. It's an element by itself. It's just C. Silicon carbide ends up being just SiC. and it's kind of in that middle between being ionic and covalent, because silicone is a semi-metal, carbon's kind of like, it's a non-metal, but it's in that middle spot. And then carbon monoxide. All right, step 2 here in our guidelines, so we're just going to follow our guidelines here. It says if an element occurs in only one compound on both sides of the equation, balance it first. If there are more than one such element, balance the more metallic one first, basically, or the metal before the non-metal. So silicone is in 1 on both sides. Oxygen is 1 on both sides. Carbon is in 1 on the reactant side, but do you see how carbon's in 2 different elements on the product side? So carbon is not going to be the first thing we balance. Okay? In fact, carbon will be the last thing, because step number 3 here says if an element occurs as a free element on either side of the chemical equation, balance it last. Does that make sense? Alright, so we have 1 silicone and 1 silicone. We're good, right? It's balanced. Alright, we have 2 oxygens and 1 oxygen. So how many carbon monoxides am I going to need? 2. Alright. And then we're now down at step number 3, where it says if an element occurs as a free element on one side, you balance it last. So carbon is the last thing we're going to balance. How many carbons do I have here? And a third one? So what do I need here? 3. So the coefficients are 1, 3, 1, 2. And if we were to write out our final last chemical equation, we would write silicone dioxide as a solid is going to react with 3 solid carbons to produce solid silicon carbide and 2 carbon monoxide gases. Okay. And we would check that it's balanced by counting the number on each side. Which is, and then we'll talk about step number 4.